All right, everyone, we're going to go ahead and get started. I just want to thank you all for joining us today for Hatfield Marine Science Center's monthly virtual Science on Tap. I hope you're someplace comfortable with some good food and some good drink. My name is Cinamon Moffett, and I'm the Research Program Manager at Oregon State University's Hatfield Marine Science Center in Newport, Oregon. I will be one of your hosts this evening. The other is Shannon Reed, who will be helping with technical issues and will be moderating some of your questions. Shannon, can you say hi so they can see your face pop up?
Hi, this is Shannon.
Perfect. Thank you, Shannon. So you might see her name in the chat box if anybody has questions, so feel free to do that. And we have quite a crew for you tonight, but first, just a few logistics. I wanted to let everybody know that this is a webinar format, so you do not have a mic, camera, or screen share, but we do hope that you ask us lots and lots of questions, and you can do that by using the chat box, which you can find either at the bottom or the top of your Zoom screen. And when you click on it, you'll get a pop-up box and you're able to put questions there. Feel free to do that at any time. I also wanted to let you know that this and all of our events are recorded, and you're welcome to go check those out. I just put in the chat box that link. So in a few days, this event will be there, and you're welcome to share that if you have anybody who is interested but wasn't able to join us. Couple of quick announcements. We will not have a December Science on Tap, which is kind of our tradition, but we will have an amazing virtual Science on Tap in January on the 12th in 2021 at 6 p.m. Sarah Hamilton will be talking to us about the impacts of sea star wasting on Pictopodia, or the sunflower sea star off of the Oregon coast. So please join us for that, and announcements will come out for that, but if you have any questions or you're looking for the link, if you use whatever platform to Google HMSC, scroll to the bottom of our page, our calendar of events is there. But for tonight, like I said, we have a cast of characters to help us tell the story of the new building at HMSC's campus in Newport. So if all of my speakers can go ahead and unmute themselves and turn on their camera so everybody can see you, I will introduce you. Welcome, everybody. Thank you. So first off, we're going to have Bob Cowen, who's the director of Hatfield Marine Science Center, kind of set the stage for us. We'll have Crystal Sanderson from YGH Architecture talking to us a little bit about how they dealt with a lot of the challenges at this particular site. Jim Lewis is going to take us deep in and talk to us about the different safety features that are built into the building. Unfortunately, you'll also get to hear from me a little bit more, and I will talk about the vertical evacuation and the way that this building functions in that purpose. And then we'll wrap it up with having Mark Farley, who is the Strategic Initiative Manager at Hatfield Marine Science Center, kind of talk about lessons learned and some challenges that we were able to negotiate with dealing with this building. At the end of the presentation, we'll open it up to questions, and we'll have a couple other voices joining us at that time. But for now, I'm going to actually just hand it off to Bob, and Bob, let you take it away. Everybody else, you can go ahead and turn your cameras and mics off, and we'll let Bob get started.
Great, thanks very much, Cinnamon, and welcome everyone again, and thanks for joining us. So tonight we want to talk about the process that we went through, the various issues and challenges, and the outcomes, how we resolve some of those outcomes in building what turns out to be the first ADA-approved vertical evacuation building in the nation. My role tonight is to introduce some of the processes that we went through leading up to the design in the building, and again, outlining some of those issues that were very clear that we were going to be dealing with. And the remaining of the speakers will give detail of how the outcomes were and how we dealt with them. The really exciting part of the building and the creative aspects of it. So if I go to the next slide, Mark. Let me give it just a real brief background. Everyone knows, I believe, Hatfield. It's a 49-acre campus. It's located in Newport, at the water's edge, which is necessary because we have a 1 million gallon a day seawater system. We also work in the ocean, and so being close to it was very important. And we have this tremendous amount of infrastructure already in place. We house close to 450 people, not just from OSU, but also 5 state and federal agencies here. And all of those people are conducting a wide range of research, academic programming, taking classes, outreach to the community, and general support that's provided to this entire ecosystem. Hatfield is now 55 years young, and it's going strong. In fact, it's doing so well that we needed to accommodate continued growth and access to the coastal environment. So as we were starting to vision the expanding of marine programming that's occurring on the coast, and particularly that associated with the Marine Studies Initiative, it was clear, next slide please, that at Hatfield, we were limited by mostly older infrastructure, and I'm not taking this particular hit here at NOAA, and minimal space availability. We simply could not accommodate new program growth because we were already bursting at the seams. We needed new space, but we also needed dedicated and state-of-the-art laboratories to accommodate the research. And next slide, please. As well as under the expanding outreach and undergraduate and graduate programs that we have here. So the major goal of this newly developing Marine Studies Initiative was to actually dare to dream of a new building for Hatfield. Next slide, please. And miraculously, we did it. We were here. We have the Gladys Valley Marine Studies building. This is truly a world-class building. It's a building that would be the pride of any major campus in the nation. And we have it here, right here in Newport at Hatfield. So we should be really happy with that. And what we're trying to do today is just give you a little bit of a sense of some of the unique qualities of it, the challenges that we went through and how we got there, and just so you have a better understanding of what's in this building. So the whole process, next slide please, was a enormous undertaking. That's an understatement. It involved many talented people across a wide array of skill sets. The design and construction team, the design team was YGH Architecture and KPFF Engineering, and the primary construction, general construction, was Anderson Construction. And then support from different facets of OSU, particularly capital planning and construction. This was my first interaction dealing at a level of building something like this. And I will say that this was the most professional, capable, and committed group of people. And what was really impressive is the degree of pride that they took in this project at all steps. So, I mean, it was great working with them. I learned a lot. It also involved, next slide, a significant outpouring of financial and political support, largely from the community. Starting out with a $20 million matching grant, challenge grant from an anonymous donor. We now know, everyone knows that it's the Valley Foundation. And they put forth a challenge that we raised an additional $5 million philanthropically from the building, as well as matching $25 million from the state in bonds. And that was a big political lift. And it really have to thank Representative David Gomberg and State Senator Arnie Rowland, in fact, the entire Coastal Caucus, for their support in that. The fact that we were able to pull all of this together in such a short amount of time was remarkable. And that also was due to the tremendous support we had at the university all the way to the top. Then President Ed Ray and Provost Ed Fazer, who came in with the final money to make this work, and an additional $10 million from the university. So I mean, lots and lots of people to thank. That's not what this is about, but it was a significant part of the process to get those ducks in a row so we could move forward. Next slide, please. So as we were accumulating the money necessary to do this, there was a lot to think about where to build this building. We certainly understood where we are. We are in a very seismically active area. We are currently in a tsunami area, and we understood that. But we also had a lot of requirements for programming that needed us to be near the water, near our existing facility. And so we looked at this from all sorts of different directions. And initially we set up an internal review committee, and that committee not only reviewed programming and some of the requirements that we had and what some other options might be for other locations, we established a set of building principles centered on safety for those in the building and those around it was important. And setting our criteria around the scale of seismic and tsunami activity that we might expect here. And then we got an external review committee. This was a outside independent group of predominantly engineers of a variety of different flavors, including several who were members of the National Academy of Engineering. To review the different information that we were gathering about siting. They evaluated all the data that was going into the models that were being used for seismic and tsunamis. So we really truly understood what type of forces we might expect at these different siting options that we were looking at. And once siting was finalized by this combination of internal and external review boards, then the external board started evaluating the outside, the KPFF and YGH's design solutions. And it became a sort of an iterative process working together to finally a concurrence about what was the design metrics that we were working on and operating on, and how were we going to address that. And that's what a lot of the latter part of this talk is about, is how do we deal with those. Then just give me tell you a few things about some of the actual seismic and tsunami considerations and some of the forces that we were going to be dealing with. The next slide, please. Well, first of all, from an earthquake perspective, a building in an earthquake environment needs to be able to withstand a variety of forces that operate in all sorts of different directions on the building. Intense lateral and vertical shaking, the ground moving around, and the stronger the earthquake, the stronger those actions, but also the longer that they last. So that continual movement tends to accelerate the breaking down of the strength parts of a building. There's subsidence, the actual vertical drop of the ground as the earth is adjusting in the seismic event. There's lateral spreading, the cracking of the ground that could happen under the foundation or nearby that might alter the stability of a building. And then next slide, knowing that we were building in an area of the harbor, near the harbor on 120 feet of sand with dredge spoils on top, there's the potential for liquefaction and basically liquefying the sediment around under the building. So those are some major seismic forces that needed to be considered. Next slide, please. The other aspect of where we live is that the local earthquakes generate tsunamis. And so we had to look at the different aspects of the tsunami, how large they were, how rapidly they occur, arrive, the direction of flow. So starting with evacuation maps that you see here, which you're all familiar with, it gives us an idea of the extent of water, but not detail about the flow or the actual depth. So next slide, we used a variety of models that actually took in specifics about the offshore bathymetry and, importantly, the in our case, the Yaquina Bay and Yaquina River topography, and bathymetry, because that really has a very specific localized effect on what the flow will look like in one of these events. And this particular figure is just one outcome, shows a very large wave hitting the coast up to 10 meters deep, and then how it dissipates as it comes into the channel and is carried down into other areas. It also flows back out, and this can occur sort of as sloshing back and forth over a couple-hour period. So we needed to understand what sort of depths we would be encountering in that, and this was just one approach to that. Next slide, please. So besides the seismic forcing, then you have forcing from the water actually hitting the building. You have the hydrostatic forces of the water just continually flowing past it, the drag or hydrodynamic drag forces that are going around the building, the impact, the initial impact or debris that's being carried by it, and even buoyant. The building itself might actually float in that situation like a boat. So all of these different forcings had to be considered if we were going to actually utilize the building after the seismic event as a vertical evacuation site. Next slide, please. So besides the tsunami hydrodynamic issues, there's the potential of, with a large ship that would be in the harbor, that it might be carried to and impact the building. And so these large debris strikes had to be considered, as well as just a lot of smaller boats or cars that might even be transferred past the location. And next slide. Taking all of those things into consideration and having a building that can withstand all that, how high did it need to be? We needed to use the rooftop to give a safe haven for people. And so we looked at, on the right side, you can see different depths of the water in different seismic events, the L to the XXL event. And our building height is close to 20 feet above the expected highest water in the largest event. So we have substantial vertical clearance in that regard. And so these are just a sort of a very quick overview of all the issues and challenges and forces and considerations on top of the basic programming design elements that we wanted to go into this building. And so now I'm going to turn this over to Crystal Sanderson from YGH Architecture, because the architectural firm is they had the creative aspect of building this building. They work closely with an engineering firm, but what I've learned is they do so much more. And so we're going to give an opportunity for Crystal to tell a little bit about the process that architects go through in the whole building design and building of a building, and then pass that on to look at some of the specific structural components and solutions that we have to all these challenges. So I'll turn this over to Crystal. Thanks.
Thanks, Bob. So I'm Crystal, and I'm an architect for YGH Architecture. Architects are what you might call, what scientists might call multidisciplinary generalists. So we're Jills of all trades and masters of none. We work with a multitude of consultants, a large team of representatives from the client. We work with regulatory agencies and contractors and take all of their expertise and we coordinate it. And we take the client's vision, in this case, the Marine Studies Initiative, and we shepherd it through planning, through programming, design, documentation, into bidding and the regulatory process, and then into its built form and construction. So yeah, we design buildings, but we're also there throughout the process, working with experts all around. So that's what architects do. I think what was unique about this specific process is that we had a very strong and innovative vision, which was the Marine Studies Initiative, brought to us by OSU. And that really guided our work for this building. so that the building is really a manifestation of what that initiative stood for, as far as collaboration, as far as innovation, and as far as engineering and making a building that can withstand a tsunami and a 9.0 earthquake. So the form really came from those goals, which was wonderful and unique from an architect's perspective. So what we wanted to do is really put that learning and that collaboration and that science on display with our design. And so yes, architects too, something we do is a lot of times we have what you would call maybe a thesis statement, what we would call a partie. And so with MSI, we had a really strong partie of putting that science and learning and engineering on display throughout the building. So you can see with the ramp how to get to the vertical evacuation. You can see large concrete cores that are withstanding forces. So I think also with this project, what was hard, what our challenges were, are pretty much everything Bob just talked about. The fact that we are really had to innovate systems and criteria to design to, because with a tsunami building, there are no codes regulating this. This is really the first of its kind in the state of Oregon. So we had to work with a third party, work with tsunami modeling and animation specialists, and come up with those criteria to design to, where we normally would not have to go through that process. And then we had to explain that process to the typical regulatory agencies, the building department, to justify what we were doing and to make sure they were aware of some of the differences with this building than what they would see with a normal building. And I think what was easy about this process has really been working with OSU as our client team. Again, the strong vision from them, and just what wonderful, really trusting client they've been to us. So that's kind of what we do in a small nutshell. And with that, I think I'll hand it back to, I think, Bob, or I'm not sure who's next there.
It's Jim.
Jim, great.
Thanks for that, Crystal and Bob. So the next thing, we're going to talk a little bit about the building. There is a process. What is deep soil mixing? That's what the root of this thing is. And that magnificent rig out there is something like I've never seen. I've never heard of this process. You can see those vertical yellow silos in the image off to the right are basically a setup of a small batch plant. And I'll tell you why right now. So deep soil mixing is a sand and cement grout mixture that's injected into existing soil by way of an auger system on that big crane rig. There's 6 augers fixed side by side that bore into the soil to a depth of 100 feet. As they're retracted, the grout mixture is blended with the existing soil and sand that forms a roughly 2.5 foot by 12 foot by 100 foot panel, which is about twice the height of the building it supports. There's about 250 of those panels that make up the grid shown in the bottom left of this graphic. And boy, that lapse time thing is sure cool to watch, because it took them months. It took them 100 and something days to do all this. And the reason is to stabilize the soil, which is all sand and silt, under the building, and minimize the effects of liquefaction, and provide a friction foundation when building on soft material to accommodate differential settlement during an earthquake. Up to 9-inch liquefaction is what they expected without deep soil mixing here. It also serves as a barrier to scour by inrushing water scouring. So it goes down 100 feet, the water's not going to undermine the building. So it's good to point out too that deep soil mixing and this substrate foundation is resistant to liquefaction, but it doesn't address mass subsidence or a vertical drop. Next slide. So the next thing are the anchors that hold the thing down. So there are around 50 deformed steel hold down rods. Think of giant rebar, varying in length 30 to 50 feet with a diameter of about 2.5 inches. And you could see the image on the right has got these giant protrusions out of the ground that are buried in these panels, and they're coupled with these enormous nuts that are mechanically fastened to the structure above. And well, you can see what color they are and maybe understand why I didn't include them in my description. But the reason they're there is to put in place to anchor the building to the deep soil mixing panels to resist any buoyancy or uplift, as Bob mentioned before. Next slide. So the shear walls and elevator cores, it's common for any floor to ceiling structure like a stairwell or elevator shaft to be used as a structural core to assist in the building's lateral strength, rotational, or just shaking from the ground up. Strategically placed shear walls aid as well. So the stair cores, elevator cores, and the shear walls in this particular building are extremely robust, as you can see. They're fortified with far more reinforcing steel rebar with a concrete mix design, significantly stronger than just your run-of-the-mill build a house kind of a mix. And these structures are also tied to the deep soil mixing below. I'll talk about a little later. So why is it like that? So the strengthened components are connected to the surrounding structure and designed to deal with lateral forces to allow some movement while maintaining structural integrity. So there's heavy mat slabs under the cores, mat slabs of concrete and rebar under the cores. They're large enough to resist the overturning of these structures should it become that violent. Next slide. So you can see that flying that giant girder in, that was a pretty exciting day. That was super cold and windy. And that was the beginning of the end of the structural concrete by the placement of that huge girder that carries the roof of the auditorium. And the slide on the right, you can see how much fun it might be being an iron worker when there's, snow on the ground. It's got to be real cold. That was a fun day. It shows this kind of labyrinth of the skeletal structure and how it relies upon. They're tied from core to shear wall back to core. Next slide. It's interesting here because they're really two buildings, and a structure this size to be built together, and the greater the area it takes up, the less of a possibility that it'll all stay together. So these were, I'm going to guess, among the maximum sizes you could have without breaking them up into two pieces. So you have two separate buildings. On the far right slide, the rectangular shape is the lab core, and then next to it is the auditorium on which the ramp is placed, and they're independent of one another. And it's tough to see in the middle. Walking through the buildings, you would never know they're two structures, but what's there is basically a hinge, if you will, that allows movement between the two without them bashing together on each other and kind of tearing themselves apart. And it's about like a 9-inch, I guess, vertical and lateral body of movement that it's allowed. Next slide, Mark. So these next slide illustrate the wall construction and cladding or siding. And these walls that you see here and all of the perimeter, really, they're non-structural. And they'll wash out during the inrush or outrush of seawater, or if they were impacted by a lateral debris strike, without diminishing the structural integrity of the building at all. So they're just pretty much standard commercial stuff. These are framed with 18-gauge steel studs. Next slide. And over top of those studs on the exterior are this waterproof gypsum or drywall, which You know, you think how waterproof is drywall, but here we are. And it's covered by this blue material, is this breathable waterproof wrapping. And atop that are fastened these green vertical parts. They're fiberglass, they're Z shapes that provide some depth for the insulation that's slid between them. It retains the insulation. And it also provides an anchor for the horizontal 1x4 shapes you see in that center photograph, to which the siding, the cedar siding, is fastened. Next slide. So the siding, there is zinc that is a standing seam zinc formed shapes. It's sheet metal that is used on roof structures, of the sloping roof structures, and all the vertical lower siding that uses zinc. I never thought of zinc as a siding material. It doesn't decompose. It just changes color over time and looks pretty magnificent after year 10 or so. The other thing that I really didn't understand and hadn't seen before was burned cedar siding. So when presented with this by the architectural team, I was kind of looking at them out of the side of my face. I'm thinking, this brand new stuff is a 1x6 piece of tongue and groove Western red cedar that's been burned and charred. And is this new stuff? And my question was, how long has this stuff been around? Are you beta testing some stuff on us? And the reply was, well, Jim, it's only been around in Japan for about 300 years and it's still being used. So we think it's going to be okay. And I humbly withdrew my concern at that point. Next slide. So this is progressive collapse. And what this image captures is the steel column supporting a horizontal girder above. And the columns are not on the exterior walls, but inboard some distance, inboard of the exterior wall. The exterior wall being framed there is a crumple zone area that we'll talk about in a second, that would yield during a hard ship or debris strike while leaving the vertical steel columns intact. So those columns are pretty frequently placed. They're basically double the amount required in a standard building. And this supports the primary structure of the building. So basically we could lose every other one or a number of them and still be okay and be survivable and potentially repairable after 9.0. Next slide. So this is the illustration of the crumple zone. So this is a softened, Mark, if you go back to the last slide. So the outer edge where that steel stud wall is being framed, that area there is purposefully less robust than the other to absorb any lateral force coming. And then go ahead and jump to the next one, Mark, sorry. And this is up on the roof where the steel railing, from the steel railing over to the parapet wall or exterior wall, that is made to crumple and yield. Primarily the railings there is to keep people, once evacuees away from the edge where any potential large debris or vessel strike would occur to keep people safe. But that would all crunch in, diminish, be damaged, but it would not affect the evacuation space at all above. And that's my last slide. And next up is our lovely and talented Cinamon Moffett.
Thanks, Jim. So I get the pleasure of talking to you a little bit about how this heavily engineered building works as a now official assembly area for South Beach area. So when the ground perhaps starts shaking now and you are somewhere near the Rogue Distillery, the recreational port, NOAA Mach P docks, or somewhere on the Hatfield campus, you have the option of getting above ground and outside of the pending tsunami wave by going to the top of the building. Safe Haven Hill and the assembly area at the community college are still options, but now we have this third option. And which assembly area you go to will depend on your personal choice, your starting location, how much time it takes you to start moving, but also your mobility. So if you do choose to go to the top of the new building, there are 3 ways that you can get to the top of the building, and they are shown on this slide here. There is the ramp, which we're going to talk more about, and Jim kind of showed you a little bit about where that was at. There's also those hardened stairs, which Jim talked about, are surrounded by the core walls that provide structure to the building, but also some flexibility if need be when the ground starts to shake. And then we also have the elevator. This elevator is accessible 24 hours a day, 7 days a week through a lobby in the building. Unfortunately, during COVID times, that lobby and our ramp are only open for emergency access only. We're all looking forward to the time when that lobby and the rooftop are open during daylight hours to everyone. But for now, it is available if we need it for emergency access. So the 3 different ways to get to the roof just provide redundancy, so that doesn't matter how you come to the building or what your mobility is, you'll be able to get to the roof. But that elevator is the thing that, as Bob said, makes this building the first vertical evacuation building that's ADA accessible in the United States. I want to talk a little bit more about the ramp specifically. So next slide, please. Well, I need to move my slides forward. Okay. So this ramp is a sloped sidewalk basically leading to the roof, and it has been specifically designed to be very clear in its purpose and to be seen from a long distance. And that is because, as Crystal was saying, the intent of this building was clear from the very beginning. And we really wanted this to be an intuitive design that led people up to the building, to the rooftop, and that they would just know that that was something that they needed to do, because as folks need to learn about vertical evacuation structures, we wanted this to be an easy kind of learning curve to know where you needed to go. And the ramp is definitely the most visible of the 3 access points. It is a little bit too steep, as you can see in this picture, to be ADA approved. So if you do have mobility issues, you definitely want to use the elevator in the lobby. Mark, can you just show us on this picture where that lobby door would be? Right there. So if you do need the elevator and you come to the decision point, that is where you would go to get into the elevator to get to the roof. We've talked about the 3 different ways to get onto the roof, but I also want to talk about what makes the rooftop special for this vertical evacuation. So next slide, please. Most of the buildings that are built in this way would have infrastructure on the roof. There would be things like roof vents and the HVAC. But because we knew we needed this space to accommodate up to 920 people for possibly 2 days, we needed a space to accommodate them. And so this building was designed with this big open flat roof. And so that would just give us room to be able to accommodate and support those folks during the event. So let's say you've had ground shaking, you've found a way to the roof is open and there's room for you. What happens next? So next slide, Mark. So up on the roof, we have a room that is filled with supplies. The supplies are basic survival. It's not fancy glamping camping, but it is a survival to support 920 people for 2 days. So that's 2,000 gallons of water. That's over 600 emergency bars. That's sanitation, communication with the city's incident command center, 27 12-person tents, personal warming, lighting, and a trauma kit for 1,000 people. All those things are in this space because we wanted to be able to support people for up to 2 days after the event. And the reason we needed to have that time scale is as we know, tsunami waves don't just come once. There's sometimes a series of them, and they're not always the biggest the first time around. We might have aftershocks. So we really wanted to be able to support people to stay up on the roof for the 2 days until we knew that the threat was gone and we could come on down and then either activate our own emergency plan or actually head up to the OCC, the Community College Cache, which is being designed as a phase 2 cache to support people for up to 3 weeks after the event. So how does this building, with all those things in place, all the things that Jim talked about, all the vertical structure supports that I've talked about, really increase the life safety at the South Beach Peninsula? Mark, can you go to the next slide, please? So on the left, you can see an updated evacuation map, and there are 3 colors there. You have yellow, green, and orange. The orange shows the worst case vertical run up on the landscape of the water for a distant tsunami. The yellow plus the orange shows the run up on the landscape of water from a local tsunami, from a local event. And you can see that Hatfield is marked by a little school. Mark, can you show us where Hatfield's at? Yeah, right there. We are surrounded by all these wonderful colors. And in the past, our choice was only to go up to Safe Haven Hill, which in this map is marked with an A. Now we have another choice. We have the vertical evacuation, which we've been talking about, as a place that you can evacuate to. So what does that do for us? On the right-hand side of this, you can see there's two different maps. The first one shows basically what would happen if we needed to evacuate to Safe Haven Hill. There are three colors shown there. We have red, orange, and green. And this is a model called Beat the Wave that was done by Ducami. And it is a daytime scenario. And it shows basically the survivability of this type of event based on how far you need to travel. And so the red shows areas around our estuary walk. And if you happen to be there when an event happened, the likelihood of injury or fatality would be high. In front of the visitor center, where you have the orange colored line, if you are 65 or older, the likelihood of injury or death would be high to get to Safe Haven Hill. And so now with the vertical evacuation building in place, you look at the one all the way to the right, you see that all of those areas are green. And so what this does is just provide a much higher level of, the location of the building is placed in such a way that we will have higher survivability after this event. And so all of us are just so excited to have this building on site. And we were really excited to share this story with you. Mark's going to take it from here and talk a little bit about some of the lessons that we've learned in this process. So Mark, I'm going to hand it off to you.
Great. Let me get myself all unmuted here. Something that okay, it's working from home. There's always children. That's going to tell you something. So one of the first lesson we learned, which was kind of an odd one, and was signage. We're all pretty well programmed to understand and see very traditional signs inside of a building. And we've all been practicing at evacuating tsunami routes outside. So you see them in cars, you see them as you're walking where you would need to go. Well, so we're inside of a building. So for the very first time, we started thinking about how do you tell a population that's inside of a building to evacuate? Now, one thing we hit right away is we have, as Cinamon mentioned, we have this ADA accessible elevator that takes you to the roof, to the evacuation space. We have all learned since we were 2 that you don't get in an elevator in case of an emergency. But in this case, you do. So you don't get in it when there's a fire. You do get in it when there's a tsunami. So right off the bat, lots of education around kind of reprogramming folks who work in this building. And then we started kind of trying to tackle what these signs should say and how they should communicate. Now, keep in mind, there are no standards for this. So this was us doing this for the first time. And we really were struggling with, you know, this person's running backwards according to international standards. What does it mean to go up if you're in a wheelchair? We came to this solution, which was trying to kind of cover all the bases in one sign. Super interesting process. Cinamon and I and OEM spent a lot of time working on this. We are convinced that we will be wrong and that somebody will come along and do a better job behind us, and we'll have an opportunity to just kind of all learn together. Other countries have international standards for vertical evacuation buildings, and this is the sign for that to indicate that this building is a vertical evacuation point. Because of the ADA aspect of the building, we had to add a symbol to it. So the wheelchair was added to this symbol. lots of interesting issues around this. So we consulted with OSU's Disability Services Center and had them help us with this, because this is a first. What is this sign communicating? We had the running person behind the wheelchair at some point, and that was perceived that it looked like they were being pushed, which was not a desirable communication point. The wave coming at the building caused a lot of confusion around, okay, is the wave coming from that direction? So there was a lot of issues around signage, and I don't know if we got it right, but this will be our kind of first swing at the problem. So if you are in the marina across from Hatfield, if you are in our housing area, if you're at the visitor center, these signs are very visible from all those locations. So this will be a slow process of kind of community education on what's that sign mean? Wait a minute, what's that? And we want people to ask those questions. And over time, and especially after we kind of exit our COVID times, inviting people to kind of participate in coming up to the roof. And as Cinamon said, our campus is closed to everything but kind of an emergency situation. So education will come after we are done with the plague. So during the process of building this building, we had a lot of media. And the media is often where people kind of express their thoughts and feelings and just kind of work out issues. So we had positive media, we had negative media. And because we're an academic institution and we are academics, we are used to a robust conversation of disagreement, that is something that we all value. So while these media articles seemed negative, we really took it in the spirit of a conversation and a critical friend. So what could we learn about everyone's thoughts and feelings that would make the process better? What could we do to educate people better? What were the issues that were on people's minds and how could we address them? And so this was an ongoing process that was kind of years in the making, and pretty interesting. So we're kind of just getting to the interior tour here, but I thought I'd cover some of the just basic stats of the building. As Bob mentioned, it took a lot of money to build this, and to be exact, it was $61.7 million. Lots of efficiencies went into this, and it came in and was produced on budget, which was something that everybody as part of the building team was very proud of. The building itself holds 28 to 30 faculty in their labs. So what does that mean? What does a lab mean? That means anywhere from 1 to 5 people that would support that faculty member, that scientist. So we've got a lot of folks in this building and a lot of space for a lot of different kinds of science teams. It's 72,000 square feet, and it's the bottom floor is classrooms and kind of the public space, the auditorium, the innovation lab, which is a new feature for us, a shop that's filled with equipment for manufacturing and prototyping. On the second story, we have an artist studio. So for one of the very first times, we're going to have a designated artist in residence that will be working in the building and just kind of trying to work with science and tell stories in a new way. We are going to have a cafe on the bottom floor, which is really new for all of us on the Hatfield campus. We are always struggling to get something for lunch that's quick and we can run in and out. So everyone's pretty excited about that. Let me see, let me move on to the next space here. So a little interior tour. One of the large classrooms that's set up for kind of interdisciplinary study. Each of these monitors represents a team. They can work on something at those tables, and then the instructor can kind of switch it up and move those projects around the room. So really training that next generation of students to work in teams to solve part of a problem for a greater whole. We're really excited about this classroom and just the kind of interesting new way of teaching that it represents. The lobby. So off to the left here, the fireplace is kind of the main entrance where that donor wall was that Bob showed you, our cafe area. and just a really lovely public space for everyone to circulate in, and lots of resting areas, lots of conversation areas, the fireplace, which everybody values on the Hatfield campus. We have an older staff lounge, and everybody always gathered around the hearth. You can see one of our evacuation signs there indicating that the stairs are accessible from this area. Another part of the lobby that goes up the main stairway to the second floor. This entrance is kind of open onto the courtyard that kind of keeps our campus, the core of the campus. Our auditorium, 250 seats. One of our 1% for art projects. This was Thurston Healy, really innovative, amazing piece that I will love to show off to you all at some point. Another nice piece, Michael Boonstrom. The Innovation Lab, which is filling up with equipment as we speak for all kinds of projects to be done around oceanography. Our shared lab spaces. Scientists share these spaces, and they have a bench. These are benches looking out onto the window, and lots of nice light going into the area. Right outside of that space is our graduate student carols. So they work in these labs and just can kind of have this respiration of activity between the two spaces, which is really lovely. All right, and we've come to questions. So Cinamon, Shannon, I think I'll turn it back to you for reading questions off.
Great. So anybody who has any questions, feel free to type it into the chat box. Bob and Jim and Crystal, can you join us? And I also want to introduce one other person who's going to join us for question and answer. We have Dan Cox from Oregon State University, who is a civil engineer and construction engineer. And his focus is community resilience to coastal hazards, including tsunami inundation in the built and natural environment. So if anybody has questions along those lines, we have a little support, so feel free to ask those questions. So the one question we have so far is, Mark, can you take us back to the auditorium really quick? We had somebody who was interested in looking at that a little bit closer. And anybody else on the line, feel free to put in any questions that you might have. We're happy to answer them. Can you go ahead and make that, yeah, full size? Mark, you want to talk a little bit more about that space?
Yeah, so this is an amazing new space for us. As a lot of you are local, know that we have a little auditorium in our visitor center, but this really brings a whole new capacity to Hatfield. So big space down below for not only speakers, but round tables to be set up and just more floor space. So 250 seats is a pretty amazing seated venue for Hatfield. This allows us to host large classes, kind of the arena style classes that we haven't been able to accommodate so far. And then also professional conferences and community events and performances. So this space really was designed to be a multi-use community space where we could really do a lot of presentations and like I said, a new capacity for us that's pretty exciting.
And also I can throw in that the lighting system is probably the most versatile that you can imagine. That light bar above has the ability to change in just about every color. The control room in the back, there's a lighting matrix that can basically turn that into a performance theater grade lighting setup and a sound system to match. So it's something we're still trying to figure out how to work.
Thank you both. A couple more questions are coming in. And Crystal, maybe you can answer this one. Can you talk about how the elevator is powered and how it's going to respond during the event?
Sure, yeah. So the elevator has backup power from a generator that's on site. So that generator is designed to kick on when the power goes off after a large earthquake potentially. And then that elevator would be on backup power from the generator and would function until a tsunami wave comes. And so so the intent is that that elevator is going to continue to function after a large earthquake. And actually those elevator cores are some of the most robust places in the building, because those are, in some places, 20 inches of heavily reinforced concrete, as Jim mentioned. And that's providing most of the lateral resistant force for the entire lab wing, the entire vertical evacuation portion of the building. So, so that's how it's powered.
And that generator, if I can jump in on that, the pathway from the generator power to its cabling to maintain power to the elevator during that is all pretty heavily armored. That the pad that the generator's on, its electrical pathway to there and from there is equally as robust as the core itself to maintain a true pathway for the elevator to operate until the water gets there.
Perfect. Mark, can you talk to us a little bit about what your plan is to get folks to head to the building, and whether we're targeting just folks at Hatfield or we're targeting tourists? Can you talk a little bit about that?
Yeah. So as Cinamon showed, the Beat the Wave model and the kind of public education that Dogami is putting out, that's going to become more of a standard for public education and kind of the maps that people receive. We also have a Tsunami trail that is based on, the building not being there. So we're updating our Tsunami trail that surrounds that South Beach kind of recreation area. So all those walking trails will have new updated signs so that as people are visitors to the South Beach area, there's just a little bit of education going on all the time. And then Cinamon and I are putting up a lot of new walking Tsunami signs around the entire area. So if you just happen to be coming by and you're very unfamiliar with the area, there's going to be a whole lot of education going on and wayfaring for you to get your bearings. And if you're not in an emergency, it will start an interesting conversation. We also have some educators with the Sea Grant program that are doing quests. So it's a family activity, kind of a scavenger hunt. And it also takes you through the whole South Beach area in a really novel and kind of fun way to have a family fun time around disaster preparedness. So yeah, there's layers of education that we are tackling.
Just to tack onto that, yep, we believe that the rooftop is a resource for those at Hatfield, but also the surrounding community. So if you live, play, or work at Hatfield, this building is an option for you to be able to evacuate to. So we had a question about what we are looking. Does this auditorium look at a screen, or what is it facing, Mark?
So we gotta find, I'm not sure which photo I'm gonna show you for that. Let's go backwards.
So to vamp a little bit while Mark's looking for a photo, it faces out a glass wall, and that storefront glass wall is, when need be, is shielded by a motorized curtain that can just dark that whole room out completely. And
it's looking at a large monitor screen. I mean, a very large monitor screen.
Yeah, there is a very large screen from a projection room above, in the back of the auditorium.
So the auditorium is this wall right here, and the windows, which are not in the photo off to the left, are doors that come out onto this big patio area. So when the curtains for presentation are not drawn, you look out into this patio area, which for events, we can have people spilling out into this area. It's all really nicely wind shielded here. So that was also something that we all looked askance at Crystal when she mentioned that she was going to stop the wind on the coast. And lo and behold, she did.
And it's complete with a fire pit.
Outside, external, yep.
So Bob, I'm going to ask this question to you. It looks like the ramp is pretty steep. Is there ways for folks to rest on the way up? Is there any benches or anything like that built into the ramp?
There are not benches. There is a railing that goes along the side of it, and people could rest against that, as well as, I suspect, if they really needed to, people would be together and they could help each other sit down for a moment, or put an arm under each other's arms and help carry people up.
And Bob, we'll just expand on that. Boy, that ramp looks perfect for skateboards and bicycles and maybe a slide or two. Can you talk about how we're discouraging folks from using that for recreational purposes other than its intended purpose?
That's an obvious challenge for us, besides educating with signs and security, keeping people off. It's, if we were to put significant impediments for a skateboard or a skate or something like that, they would also be serving as impediments to someone who might be in a wheelchair or just even trying to walk up. So we're going to try right now with just education and trying to keep people off. But if necessary, we will find some other gating or something that will allow people in, but not their skateboards.
All right, we're getting close on time, but we just got a couple more. Another elevator question, Crystal. Can you tell us how long it takes to travel from the bottom to the top?
I think in the programming stage, very early on, I probably could have told you exactly the length of time. However, I can tell you that we planned for within 20 minutes to be able to get 200 mobility impaired people up to the roof through the elevator. I can't, for the life of me, remember exactly how long it takes to go from the ground level up to up 3 floors to the roof, but we did plan for 200 people to make trips in that elevator.
That was the primary metric, was the number of people we could get up. So it's very fast. Cinamon, if I can answer one other, I see here,
sure. We
use tsunami research at OSU, and absolutely we did. And as Mark indicated, we are a university. We are used to looking and receiving input from a variety of different sides, criticism, and we take it as a way of building our knowledge base. And so the internal and external review boards utilize that information from the research at OSU to help set the parameters in terms of seismic forces and tsunami forces. So they were that information they provided was part of that input.
Thank you, Bob. I missed that as they were rolling in. I think we have time for one more question. So this one's for you, Jim. Can you tell us the grade of the ramp?
The exact percentage of grade, I don't know. Crystal would know. However, what I do know is that the pitch of that grade was within FEMA's criteria for an evacuation ramp, but far steeper than, our ADA criteria, which is much shallower than that.
And it's actually terrible for skateboarding.
It's 1 to 4 was FEMA's max, so it's less than that. And actually, the path to Safe Haven Hill has portions that are also that steep, but it's based on FEMA guidelines for vertical evacuation.
Perfect, thank you. So everybody online, thank you so much for joining us. Bob, do you have anything to wrap us up and take us to our evening? Well, any last thoughts?
I would just thank everyone for joining us on this. We can tell we are extremely proud of this building and proud of all the people that participated in it. And I thank everyone that was on the panel tonight for their great presentations and the wonderful questions that we got. And we'll answer more. If you want to catch us on email later on, that's great. We'll try and help you get the answers to you. So thanks very much, everyone. And thanks, Cinamon, for organizing this.
Thank you, everybody. And just remember that Science on Tap will not happen in December, but we'll see you in January. So everybody have a wonderful evening, and thank you so much for joining us. And panelists, thank you so much for giving your time to share with the community. Much appreciated.
Thanks, Sam.
All right, everyone. Thank you so much. Good night.
Bye, everyone.
Bye.
Hey, Dan, thanks for being there.
Yeah.
Moral support.
It was good. Learned a lot. Thanks, guys.
That was great, everyone. Really good job.
It was nice to know you were there, Dan. I didn't want to get hit with something that we were unable to answer. So thank you so much.
Fantastic presentation. I really enjoyed it. I've been dying to come out there, so soon.
You let us know, and we'll give you a great tour. I mean, it's just so much fun. It's just
Awesome.
great.
Excellent. Have a good night, everybody.
All right.
Thank you.
All right. Thanks, everyone.
All right, I'm going to end everything. Good night, everyone.